Welcome to the first part of a two-part video set dedicated to electrical diagnosis. In this video, we're going to get hands-on and show you how to troubleshoot a fairly common electrical concern, and everyone's favorite, a short circuit. After watching this video, you'll be able to use a digital volt-ohm meter correctly, read a wiring schematic to locate components and connectors, use the wiring diagram to plan a troubleshooting strategy, and test electrical circuits using the voltage drop and divide the circuit methods. Now that you have a basic understanding of electricity and circuits from watching the previous videos in this set, it's time to use that knowledge on the vehicle. But before we get started, let's take a moment and review the primary tools you'll need to troubleshoot electrical concerns: the digital volt-ohm meter and the wiring diagram. The best tool for troubleshooting electrical circuits is a digital multimeter. Some technicians refer to a digital multimeter as a digital multimeter or digital volt-ohm meter, but a digital multimeter goes further, allowing the technician to also test amperage and diodes. Think of a digital multimeter as an electronic ruler. It measures volts, amps, and ohms. If you've never used a digital multimeter, or you're not sure how to hook one up, take a look inside the box. You'll see an instruction book that shows you the step-by-step procedure for measuring voltage, current, and resistance. Now here's a few key points that we covered in the second video to keep in mind when using your digital multimeter. When measuring voltage, make sure the leads are connected with the correct polarity. If you get a negative voltage reading, you probably have the test leads hooked up backwards. Red always goes to the most positive side of the circuit, and black to the most negative side. Measure before the load to find the source or battery voltage. And across or after the load to measure voltage drop. When measuring current or parasitic draw, always break the circuit and connect the meter in series. If breaking the circuit isn't practical, use an inductive probe. Never measure across a power source. You'll blow the meter fuse or damage the meter and possibly sustain a personal injury. When measuring resistance or continuity, make sure all power to the circuit is off. A circuit with current flowing through will damage your meter and may cause personal injury. If you're measuring the resistance of a component, isolate it from the rest of the circuit so you don't get a false reading. A reading of near 0 ohms means there is continuity and very little resistance. Sometimes this can indicate a short circuit if there is continuity to ground. And finally, if the meter display shows OL, it means there is so much resistance the meter can't measure it. This is an indication of an open circuit. Just like your trusty digital multimeter, the wiring diagram is also a diagnostic tool. Wiring diagrams illustrate how the circuits are designed and where the components are located on the vehicle. If you're not familiar with a wiring diagram, always begin with the General Information section of the repair manual. The General Information section usually explains how the wiring diagram is organized, and it shows you how to read a schematic step by step. As we saw in the earlier video, this section will help you understand the meaning of the various numbers and symbols like connector codes, ground points and numbers, wire color codes and connector symbols. And it even shows you where wiring harnesses and components are located on the vehicle. Spending a few minutes reviewing the General Information section will help you to fix it right the first time. Let's take a look at how we can use the information in the wiring diagram to troubleshoot a problem with a vehicle that has an inoperative engine coolant temperature gauge. The first step of the troubleshooting procedure is to use the index of the repair manual to find the correct wiring diagram or schematic for the coolant temperature gauge circuit. Some repair manuals offer multiple indexes, such as an alphabetical index in the rear of the book and a separate index in the electrical section. Either way, you can use whichever is easiest for you, as the results should be the same. Because the gauge is part of the instrument cluster or combination meter, let's go to that page. This diagram shows the whole instrument cluster. Since the other gauges and indicators are working normally, we can eliminate everything else on this page and focus on the temperature gauge circuit only. There, that's better. On most wiring diagrams, the power source is always at the top of the page, and the ground is at the bottom. Let's start at the top and trace the power side of this circuit. From the positive battery terminal, current flows through the main fuse, the ignition key fuse, the ignition switch, and the meter fuse to the gauge. On the ground side, current flows from the gauge through the engine coolant temperature sensor and goes back to the battery through the ground return path. Now let's analyze what we know about the circuit. This is a simple series circuit protected by 3 fuses. The circuit is controlled on the power side by the ignition switch. But it's also controlled on the ground side by the engine coolant temperature sensor. The sensor is a negative coefficient thermal resistor, or thermistor. As coolant temperature increases, resistance in the sensor decreases. The next step is to test the circuit at a point that gives you the most information with the least amount of work. We call this dividing the circuit. By looking at this diagram, the best place to divide this circuit in half is at connector B1-31. This is where the harness connects to the sensor. If we measured voltage at this connector with the ignition key on, our reading should be close to battery voltage. We have a reading of 12 volts. That means this portion of the circuit up to the thermistor is okay. If the voltmeter reads 0 volts, the problem would have to be between the sensor and the battery. Because we have the correct voltage at connector B1-31, the next step would be to check the remaining half of the circuit, which is the ground side. We can use an ohm meter to check the resistance of the sending unit. We found the problem. The sending unit is open-circuited. As you can see, dividing the circuit can really save you a lot of time. The trick is picking the best place to make your measurements. We've covered the basics of an automotive circuit and how it operates. But one of the most useful things to learn when troubleshooting electrical is the concept of voltage drop. All loads, like motors and light bulbs, are designed to consume a certain amount of voltage in order to operate. A 12-volt light bulb uses or drops 12 volts to work. The term dropping voltage means using voltage. This type of circuit is called a series circuit because there is only one path for current flow. And current must be flowing for voltage to drop. If the circuit is open, there is no path or track, so there can't be a potential voltage drop because there is no current flow. In a simple series circuit with one load, when current flows, you'll find voltage between the battery and the load. But there is no voltage after the load. That's because all of the circuit voltage has been dropped across the bulb, making it glow. When a circuit has two loads in series, each load drops part of the voltage, depending on the size of the load. The largest load, in terms of resistance, will drop the most voltage. In this case, each load is the same, so the voltage is split equally between the two. When a circuit is working correctly, there should be no voltage after the last load. Unwanted resistance, such as corrosion on a switch or connector, becomes an unwanted load that robs the circuit of voltage. The factory bulbs are dim because part of the voltage they need is being dropped across the corroded connector. So voltage drop testing a circuit could really tell you a lot about the circuit. It's kind of like looking for a voltage leak in a faulty circuit. The idea is to make sure the circuit voltage is only dropped across the load. In the last segment, we learned that loads must consume or drop voltage to operate. And voltage drop testing could quickly tell us where the voltage was being used in a circuit. Let's now use a voltmeter to make the most common voltage drop measurements. There are two ways to measure voltage drop in a circuit. The first method is to place your meter leads here and measure the voltage before the load. Then measure after the load and subtract the last measurement from the first. 12 minus 0 is 12. Our voltage drop across the load was 12 volts. The second method is to place the meter leads directly across the component. The red lead goes to the most positive side and the black lead to the most negative side. Now we read 12 volts directly from the meter without doing any subtraction. If the voltmeter leads are switched around, then the voltage measurement would be negative. So if you see a negative voltage reading, switch the red and black leads and measure again. As we said earlier, when two loads in a circuit are in series, each load drops part of the voltage depending on the load. In this example, both loads have the same resistance, so the voltage drop is the same on both loads. Here's an important rule to remember when troubleshooting. The total voltage drop across the circuit loads must equal the source voltage. Each load in this circuit dropped 6 volts because their resistance values are the same. If you add the voltage drops together, they equal the source voltage. 6 plus 6 equals 12. Our source voltage is the battery and it's rated at 12 volts. The load should drop most of the source voltage, but sometimes the other components in a circuit will drop an extremely small amount of voltage, almost zero. Typically, the voltage drop across connectors, switches, and grounds should not exceed 0.1 or 1/10 of a volt. With some electronic circuits, these small drops can add up. That's why you need to have a good ground connection. Let's take what we know about voltage drop testing and try it out. In this circuit, the bulb works, but is very dim. Because the bulb is working, we know the circuit is complete and current is flowing. If we measure our source voltage, we see it's 12 volts. But if we measure the load, the voltage is 8. Our bulb needs 12 volts, but it's only getting 8. This means that something else in the circuit is using 4 volts, because the circuit load voltage drops should equal 12 volts. Let's do voltage drop tests on the other parts of the circuit to find the culprit. The voltage drop across this switch is 0. No problem here. Let's check the ground point. The voltage drop across this corroded ground point is almost 4 volts. 8-volt drop across the load and 4 volts across this ground, that equals our source, 12 volts. We have a bad ground. Remember, the voltage drop on the ground should be close to 0 or no more than 0.1 volts. Anytime you measure voltage across a single load in a series circuit and it's not 12 volts, then that means there must be something else in the circuit stealing the voltage. Let's look at a real-world example of electrical troubleshooting. According to the repair order, the driver's side window won't open. It was working fine until last week. The driver's side door glass opens and closes perfectly. To troubleshoot an electrical problem, it helps to have a sound diagnostic strategy. A sound diagnostic strategy should include steps to verify that a problem exists, isolate the cause of the problem through testing, repairing the cause of the circuit fault, and rechecking your work to make sure the problem is fixed. Start by verifying the customer's concern. Then look at the wiring diagram. To find the correct schematic, use the repair manual index. In this case, we're looking for the power windows. According to this schematic, there should be voltage to the power window switches anytime the ignition switch is on. And both motor windings are connected directly to ground when the power window switches are in the off position. Next, let's divide the circuit at a point that's easy to get to and will give us the most information. Looks like the best place to split this circuit is at connector K1-01 at the power window switch. Since we know the driver's door glass is working fine, we can eliminate this portion of the circuit. That means our problem has to be in this area. We want to do a voltage drop and not a resistance check because we want to check the circuit while it's operating under a load. Based on this wiring diagram, we should place the red lead of the digital multimeter on the brown wire terminal coming from the ignition switch. Then place the black lead on the black wire terminal of connector K1-01. Because the power window switch connector is located under the console, we'll need to install back probe adapters so we can take our measurements. With the ignition switch on, we should read close to battery voltage. Well, that check is okay. That tells us we have battery voltage available at the window switch. If our reading were close to 0 volts, we would suspect an open circuit or a bad power window motor. If that were the case, the door trim panel would have to come off for further testing. For the next check, we'll move the red lead to the red-green wire terminal on the switch, and the black lead to the black wire terminal. This allows us to read the voltage drop across the power window motor. The reading is 0 volts because the power window switch is in the off position and the circuit is open. Think back and remember the rule on voltage drops in a series circuit. The sum total of the voltage drops across the loads should equal the battery or source voltage. When we move the switch to the closed or down position, our voltage should be pretty close to battery voltage. That's because the power window motor is the only load device in the circuit and should consume most of the battery voltage. No change. We're still reading 0 volts. We've isolated the problem. This means the switch that should be closed is still open. But let's say if the voltage reading was less than expected, say about 10 volts. What do you think that would mean? Think back to Ohm's law. You'd have to suspect that something else in the circuit is stealing voltage that was meant for the window motor. Any additional resistance would cause the door glass to operate slower than normal. Once we've isolated the cause of the problem, it's time for the repair. Let's install a new window switch and check the voltage drop. Rechecking our work ensures that the repair fixed the problem. With the switch off, nothing has changed. We still read 0 volts. But when we move the switch to the closed, window down position, notice how the voltage drop is almost equal to battery voltage. So the problem was a bad window switch. We actually found it pretty easily. With a sound diagnostic approach and using our knowledge of electrical systems to isolate the cause of the problem. In this video, we looked at how to read a wiring diagram, how to use the information in a wiring diagram to isolate circuit faults with a digital multimeter, and how to use the voltage drop and continuity test in diagnosing real circuits. In the second part of this diagnostic video set, we'll look at some more tests that you can do to isolate electrical system faults and how to repair wires and connectors. Thanks for watching.